Hey everybody, this is Larry. This is the 29th day of the June Leetcode Daily Challenge. Hope you're having a good end of the month. It's been a long journey, but hopefully you get the last couple of days and have done it all. Anyway, so today's problem is unique paths. And also, just to be clear, I'm going to go over the explanation first. The live coding portion will be at the end. I recorded in opposite orders. This is the format that I'm trying out. Let me know what you think. Let me know how you feel. Hit the like button, hit the subscribe button, and join the Discord to hang out and ask about different questions like this. Yeah, so unique paths. So this problem is straightforward in the sense that it's a very well-studied problem. If you don't have trouble with it, it's going to be a little bit tricky. I recommend having practice a couple of dynamic programming first. But the idea is that, and there are a lot of mathematical things about it. There's a combinatorial solution. So if you Google the answer, you may be able to come up with it's some variation of choosing n over m or something, or in this case m plus n over m plus n choose n or m, something like that, right? So there's some mathematical formulas, and from that you could do some maths, but and that's fine, because if you feel like that's all you need to learn, all the power to you. But I'm going to go over the dynamic programming solution for today, and the way that I want to solve this is with dynamic programming, and the way that I implement it is from bottoms up. But just to kind of go over a little bit, let's say we start with how many. So the question you always want to ask with dynamic programming, either top down or bottoms up, is what do you want to do at any given moment. And even before that, the question is, what question am I asking at this moment? And in this question, and the way that I would phrase it is that, okay, starting at 0, 0, or 1, 1, depending on how you want to do your coordinates, how many ways are there get to m by n, right? And well, there are a couple of ways to do this. So let's say you start at 0, 0 and you go to 0, 1. So that's one way. And then the other way is just going down, right? I don't know how to draw downwards. Oops. So downwards to 1, 0, right? So those are the two choices you get to make, right? And what happens when you make those choices? When you make a choice, you get to choose, you have a new problem, a sub-problem, if you will. And the sub-problem now is asking, well, how many ways are there to go from 0, 1 to m n, right? So and then you just keep on counting it that way. And from here, to kind of bring it all together, how many paths are there to go from 0, 0 to m comma n? And the number of total ways is just, okay, the number of total ways is if I go left first, and then plus if I go right first, right? So those are your two possibilities, and you always have to choose one of these for this problem, because that's the problem constraint. So from that, you just sum it together, and that's all you have to do for this problem. So one thing that I would point out, and then after that is just implementation, watch the live portion to kind of go over it a little bit more. I think one thing that I want to point out a little bit that I find interesting, and maybe it's obvious, but I want to point it out because for certain harder dynamic programming problems or memorization problems, it is not true. But I want to point it out so that you get to exercise the part of muscle where you maybe notice this but not really think about why. But so the question I want to say is that, okay, let's just say you go to some other, let's just say xy, right? So now you have some xy coordinate, and you're going to some, or you want to get to mn, right? Something like that. And you ask yourself, well, so there are two ways to ask this question. And what I mean by that is that I'm starting on xy. How many ways are there for me to get to mn, right? So that's kind of one formulation of this dynamic programming. And then the other form, so let me write this down before I get next to it. How many ways are there to get to mn from xy. And another kind of interesting observation, and you may even do this without realizing it when you write it with bottoms up or something like that, or certain types of problem, is, well, actually, we can make one observation, which is that, well, we don't, we can all so you have a rectangle, and you can actually move the coordinates however you like, right? And as long as you move the left, or you move up in the same number of steps, and the left in the same number of steps, you get the same answer. So by making that observation, you can actually say that you're trying to answer a subproblem of 0, 0 to m minus x and minus y, right? And then the question behind that is, if you want to say it out loud, which is what I like to do because it helps me visualize and really focuses on the problem, which is how many ways are there to get from 0, 0 to m minus x and minus y, right? And this may be obvious, this may be trivial, but it allows you to set up your problems in a way that is also, just a deeper understanding of, well, how you can do it in different ways. Because now, from this, you can note that, well, 0, 1 to mn is also just equal to 0, 0 to m and minus 1, right? So now, the point of all this elaboration is just to show that, okay, what does this mean for us, right? That means that in theory, if you write a top-down dynamic programming, you can write, f of mn, so you can go both ways. So you could go to f of 0 is equal to f of 1 plus f of 0, 1, or, and let's make the m and n explicit in this case. Right? So f being the distance function. And then another way to write this, of course, is you still have the same function. It's just, 0, 0, m minus 1. M and minus 1, right? So now you can see why that these two formulas are equivalent. And what I want to leave you with is that when you understand this problem and why these things happen, and when you read other people's solution, you may see different variations like I've showcased here, and implementation wise you may wonder why they are, and maybe you get a little bit sloppy in the future when this is the case in this problem, but this is not the case for every problem. And when that happens, this allows you to figure out the properties of why this is true for this problem but not for another problem. Anyway, so that's the explanation portion of it. Stay tuned for the live portion right about nowish, but I just wanted to get this across so that you kind of have an idea. And playing with, because dynamic programming is really hard, I just want to get all these ideas in your head to play with and maybe revisit in the future when you understand the problems a little bit more. And this is a little bit of a easy problem, quote unquote, so that it helps you kind of visualize these kind of variations and understand why they're equivalent. And yeah, cool. And anyway, my live portion will start right about, let me find the button, now. Hey, so this is the live portion of me trying to solve this problem. Let's get to it. Unique paths. Okay, unique paths. A robot located on the top left of an M by X grid. The robot can move either down or right at any point. How many unique paths are there? Okay, so this is a straight. Okay, so this is a straightforward dynamic programming problem, and that's probably how I'm going to solve it. Also, there's different ways to solve this. This is also a conceptually easy combinatorial problem because you could just do the math where you have the Pascal's triangle and then one distance away. So yeah, so then you have a Pascal triangle and you just keep on going and so forth. But I'm going to do it with dynamic programming because why not? It's a good practice. So yeah, let's play around with it. Which one is M and which one is N? I guess it doesn't really matter. We start at 0 or 1. Okay. Okay, and then now we just go through it. And of course, this being dynamic programming, I'll have a link below to link to my other dynamic programming video where I break it down how to go from top-down memorization to bottoms-up dynamic programming, and then to the space optimization, which I will not do for the stream, but hopefully it will give you the tools to do it. Yeah, so basically, what am I doing? Okay. Grow in range of M, for car in range of N. But the idea behind the dynamic programming is that, and I'll probably will explain it, or have already explained it, so this is just a programming portion. But yeah, we have to set the count of 0, 0 to 1, and then it's just this. Yeah, now this is standard-ish dynamic programming, summing up previous states, and the idea is pretty straightforward. Once you've done it a few times, or lots of times. Yeah, and I'm not sure about this, to be honest, in the sense that the border condition, like should I need +1 or minus, but, and we could kind of see it, right? So 0, 0 is here, so here's 1, 1. So yeah, I think this is okay. Maybe. Okay, maybe not. Why does that go out of bounds? If rho is greater than 0, because of 0. What? Do I have a typo anywhere? Oh, I mixed my M's and N's. Yeah. Okay. The Python syntax for declaring a matrix is a little bit awkward. So yeah. Okay. Oh yeah, and I have to change this back as well. In this case, I am taking advantage of the fact that I don't know if that's good. Oops. I'm taking advantage of the fact that this is actually symmetric, so that's why I'm doing a little bit really nearly. What I mean by that is that the answer for M3 is equal to 3 and N is equal to 2 is 3. But the answer for, if you swap them, it gives you the same answer, which is N is equal to, or M is equal to 2 and N is equal to 3. Okay, N has to be less than 100. Whoops. Yeah, now we're just doing some testing. Looks okay. And since the answer will be less than 2 billion, we could just submit, I think. And yeah, so that's what I have for this problem. This is very straightforward dynamic programming. That's what I have for the programming portion. So there are a couple of things you can do with this. One is noticing that, well, what is the time space complexity? Well, the time complexity for this problem is O of n times m, and also the space complexity, because, well, that's the space we have. The question may be, well, how did how can you optimize this, right? So you could actually get the space down to the smaller of m or n, and the way that you do that is by noticing that, well, here, for every row we only do this loop, and for every row we only look at the -1. So we can actually, we don't go beyond the -1, right? And what I mean by that is you don't look at row -2 or anything like that. So anytime you increment row, you only need the previous row. So taking advantage of that, you could get the space optimization down to the min of m or n. Again, I'll have the link below on my general dynamic programming space optimization video. And yeah, let me know what you think. That's all I have for this problem, and I'll see y'all tomorrow. Bye bye. Have to find a button to press. Bye bye.